Hello everyone, and today we're going to be talking about practical applications of particle filters. So in the last video we covered some of the theory behind what's going on and kind of the key components. But how do you actually use one? So we're going to be using a particle filter for localization in our task. So the way it's going to work, so we have the 6 different Aruka markers around the field, and those will give us essentially a position estimate of our robot. So let's say I have some robot here, and then I can see this marker here, and then I know some idea that like my robot's here with some probability. So we're going to represent that to figure out where a robot is, and then we're going to use our wheel encoders to figure out how probable particles are given our current motion of the vehicle. And the final thing, our motion model will be based on our controls. So if I'm going to drive the robot forward, the particles will move forward. If I'm going to rotate in place, the particles should rotate in place. And using this, what we can do is we will be able to track our robot as it drives around this entire course. This is what our actual filter looks like. So we have our particles, which is going to represent our position in the X, position in the Y, our psi here, which represents our yaw. We're going to have some velocity in the X, so that's our body velocity, how fast we're moving forward in the body frame, and then a yaw rate, which is essentially how fast we're rotating. So the actual motion input will be applied on Vx and psi dot, so our yaw rate. And our odometry measurement will also be readings on the same values. So if I have a particle that has a really high Vx, but I'm not actually moving that fast, what this measurement will tell me is that particle is not very likely. And then we'll have some Aruka measurements, which are fiducial markers around the course. And those will give us a reading on the position of the X, Y, and the yaw of the robot. So often you're not going to see things as nice as this particle filter because we have a direct measurement on every part of our state. Often we won't have direct measurements on our states and we'll have to infer them through other parts of the state. So the first issue that you run into with particle filters is, okay, cool, I have a bunch of guesses. Well, how do I set up those guesses initially? What should be the initial distribution of those guesses? So that depends a lot on your application. So for our application, we're in a 2D plane and our robot can have some essentially position and it's going to have some yaw. But we can pretty much assume that our velocity in the X and our yaw rate is going to be 0 because our robot's not going to start moving. So what you want to do is essentially set up particles around the entire course. So you just want to put these particles all around. And the reason we're doing this is because we have nothing that tells us where our robot should be. All we know is that it should be on this plane. Therefore, it is equally likely to be anywhere on the plane, and that's how we initialize our particle filter. Our particles start all over, and then over time they'll converge to our actual state estimate. So the next thing we talk about is the number of particles. So the rule with particle filters is more is always better. But honestly, a real-time algorithm is way more important. So it's not really helpful to have a really accurate state estimate if it can only tell you where you were an hour ago and can't tell you where you are right now, because oftentimes you want to make decisions about now and not an hour ago. So the way you can think about this is if we have too few particles, let's say I have something like 2 particles, and my sensor reading says that I am here, well, both those particles are pretty low probability, and there's not really a good chance that they're going to move in the right direction. So we want to have more particles, and essentially what you need is enough particles to cover your state space, but not too many that you slow too far down. There are different tricks to get around this, like parallel computation and other things. You'll want to treat number of particles like a hyperparameter and just play around and see what works best. So another trick that you want to add in particle filters is this thing called adding additional noise. And the reason that you're going to do this is because it helps the particle filter initially converge and remain with a state estimate. Because remember that we don't have perfect estimation of how our robot's moving. So let's say we have some x0, which is our initial distribution. And then what we want to do is we want to move it. So we're going to move it based on our motion model, and we get some larger ring of uncertainty because we've moved. But our sensor model is telling us that we're right here. So what will happen is over time we'll eventually converge to it. Sometimes it's really nice to add more noise than you think should exist in the motion model, because then you'll get some kind of uncertainty like this, and it'll tamp down based on your actual sensor reading. So now you'll get some representation like that, which is much closer. Obviously this is a tuning thing and just depends on your application. And often you can just kind of set it to the right value and see what converges and play around with it. So the other thing to play around with tuning-wise is the measurement model tuning. So again, just like with the motion model, technical physical accuracy is not always the goal here. While you want to represent the probability distribution correctly, oftentimes it's better to have a converged filter than a diverging filter. Because when your filter diverges, you just get nothing useful. So let's talk about a little bit why that makes sense here. Oftentimes with your measurement model, it's helpful to have higher covariance than you think you actually need, because that'll allow your filter to converge faster and be a little bit more stable. So let's say I have the two representations here. So over here, I have what is actually true, what is my sensor reading telling me how accurate it is, and here I have one that's a little bit larger. And what's helpful about this is if I have particles like this, often you get into numerical issues because only this one is really probable given our sensor reading. The other ones are still pretty close, and this will often result in some numerical instabilities. We can increase the covariance, and by doing so, we'll get a little bit smoother convergence of our particle filter. Playing around with the measurement covariance is often a good way to make a particle filter work better. The final trick, which is kind of a hack, and really just due to problems in numerical stability, reducing low probability particles. So essentially what I'm going to do is I'm going to take all my particles, I'm going to sort them, and I'm going to say anything with a probability below this, like the top bottom percent, I just want to eliminate. And this prevents it from converging to a low probability particle. So these are some of the tips and tricks about tuning particle filters. Now there are definitely other ones that I haven't covered and things that work better or worse in different applications, so always look around for what people are doing in your field.